Good morning, good afternoon, and good evening, everyone. Dear authors and invited guests, welcome to Technical Session 11A. I'm Sanskriti Khamkar, and I will be moderating this session. On behalf of the Global Knowledge Research Foundation and GR Scholastic, it is my pleasure to welcome you to the last day of the 11th International Congress on Information and Communication Technology, that is ICICT 2026, London, UK. I hope you find today's session engaging, informative, and insightful. In this session, we have six presentations. Each presenter will have 12 minutes for their presentation, followed by 3 minutes for question and answers. I will give a gentle reminder when 2 minutes remain. I request all participants to stay connected until the closing remarks. If you have any questions or updates, please feel free. Please feel free to share them in the chat box. I'd also like to apologize in advance for any mispronunciation of names during this session. Before we begin, I'd like to introduce our session chairs. We have Professor Malinka Ivanova, who is an associate professor at Technical University of Sofia in Bulgaria. Her research interests include e-learning, personal learning and adaptation, technology-enhanced learning, intelligent technologies for learning and teaching, Web 2.0, and social networking, security and privacy. She is author of many papers published in conference proceedings, journals, and book chapters. Welcome, ma'am. Would you please like to share a few words with us?
Dear colleagues, it's my pleasure to be a chair of this wonderful session. As you understand, I have many good and rich experience at this conference, ICICT, in London, UK. So I wish you one very successful and pleasant session, and maybe we will have some contacts to share, some ideas, or maybe to be involved in different projects. So I wish one very useful and pleasant session, and we can start.
Thank you, ma'am, for encouraging words. This session is co-chaired by Dr. Vijayata Kumar, who is a professor and head of Department of Computer Science and Engineering at Jaipur Engineering College and Research Center in Jaipur, India. She has 17 years of teaching experience and holds 2 Indian patents. Her areas of expertise include ad hoc networks, wireless sensor networks, and Internet of Things. Ma'am, would you please like to share a few words with us? Okay, let us proceed with the presentations. Our first author is Joy Carpio, who is presenting Control Implementation on Production Vehicle, Speed-Based and ACC-Based Approach.
Hello, thank you for the introduction. Should I share my screen now?
Yes, please.
Okay. Are you able to see my screen now?
Yes, it's visible.
Okay. All right. So good morning, everyone. Today I'll be presenting a practical approach to implementing speed control on production vehicles without requiring privileged manufacturer access. But before that, let me just quickly introduce again myself. I'm Dr. Joy Carpio. I finished my PhD at UC Berkeley, and I'm presenting this work on behalf of my partnership with National University Manila, Philippines. So, traffic instability remain a major challenge in mixed human automated traffic, while many control strategies show strong performance in simulation. Translating these controllers to real vehicle is difficult due to limited access to vehicle actuation. This creates gap between algorithm design with real world deployment. This work focuses on practical ways to actuate production vehicles and bridge that gap. The challenge is no longer designing controllers, it is deploying them. So, in this work, I compare two practical speed control strategies. The first is directly commanding the vehicle via torque and brake injection. And the second leverages the vehicle's built in adaptive cruise control by emulating button presses. The goal here is to understand the trade off between precision and deployability. For this work, we assume that CAN access is available through the OBD interface. However, write access to powertrain signal is often restricted by cybersecurity gateways in most newer technology vehicles. This leads us to trying two actuation paths. So the first one, as I mentioned in the previous slide, the direct control through torque and brake commands, or the indirect control through ACC interface. Let's get started with the speed-based approach. This approach directly controls vehicle dynamics. Speed is tracked through an acceleration command, which is translated into torque and brake signals. This approach is called speed-based because we directly adjust the speed, but the adjustment is through torque and brake injection. Thus, this control strategy is via acceleration command. There are two key components in this control strategy. One is the speed tracking on the left side, and the other one is the gap keeping. I'm showing it on the right side of this slide. A PD controller is used here for speed tracking with bounded acceleration. The gains of this PD controller is designed for speed tracking. It is tuned using the idea of ensuring the vehicle speed to transition within 1 second. Based on the field test that we observed, the maximum allowable acceleration that we recorded is 4.5 meter per second squared, about that value. And so this becomes our upper bound for this acceleration boundary. For any target speed change above 4.5 meter seconds, the transition time can exceed 1 second. That's how we design this speed tracking control. Now, moving forward for the gap keeping is incorporated using a safety distance derived from a stopping distance, where the stopping distance here is obtained from a conservative assumption from uniform linear acceleration kinematics. We also use a PID controller to model the acceleration command when in the gap keeping mode. Controller gains here for this PID controller were tuned using simulated leader-follower scenarios before real-world deployment. Now, for the system architecture, using this approach, we wanted to highlight the requirement of bypassing the cybersecurity module to allow write access so that we can inject torque and brake pedal command. Thus, this approach requires, hold on, deeper system integration. The upper block here on the left side on the hardware architecture, the upper red block here shows the usual way on how we wanted to connect from the EOCM to our computer, for example, via the OBD port. And while the lower red block here, right here, if you can see my cursor, shows how we wanted to do it instead, so we can execute write access to the EOCM. Take note, because newer technology vehicle has this cybersecurity gate module, we are unable to write directly to the EOCM of the car. It keeps on blocking that, serving like a firewall. And so we have to do some modification on the hardware architecture of the car so that we can send our write access or write signal towards the car. Now, on the software side, we use a ROS pipeline handling the decoding, control computation, and command transmission. One important thing that I wanted to highlight here is that since we bypass the CGM, and take note, CGM module sends a heartbeat signal to the EOCM, telling the EOCM that everything is okay. We need to emulate that heartbeat so that the EOCM thinks that everything is okay and that it will not stop the publishing and receiving of CAN messages in the car system. Now, the key elements to this design is to determine how much torque and brake pedal signal is to send to the EOCM, since these are the control inputs that the car takes to adjust its speed. In general, the controller designed for autonomous driving outputs acceleration. This being said, we need to create a relationship between acceleration value to its equivalent torque and brake pedal signal. For the data we collected, we observed a near linear relationship between acceleration and engine torque. And so from there, we try to obtain this equation mapping positive acceleration value to the equivalent torque signal. And then similarly, the braking behavior, uh, we realize that this can be approximated from negative acceleration and the brake pedal angle. So here we model the brake pedal angle with respect to the negative acceleration value. This simplified models enabled real-time control without complex vehicle dynamics. To see the performance of the speed-based approach, we automated the target speed of so we let the car drive using an automated target speed that we inject to the car. So it basically tries to follow an increasing step input so that we can evaluate the transient response of the controller that we designed. And as a result, as you can see on the left side plot, we observed that the controller achieved a fast settling time when trying to track target speed with a small steady state error. And we can say that the speed tracking is in the acceptable regime. Then we also recorded the leader vehicle distance. So while the car is trying to follow a leader vehicle, we recorded the leader vehicle distance obtained from the CAN via the radar sensors or the camera sensors that is built in the car, which we can access on the CAN bus. And we compare it to the calculated desired gap that we defined for our controller. From that, you can see on the right side plot that the gap keeping tends to be conservative on the way we designed it, with an average discrepancy of under 1 meter for the entirety of the driving data that we collected. So overall, the approach works. That's what we concluded, but the behavior must be tuned. So a lot more work are still needed to have a better performance for this approach. Now let me move forward to the other approach that we explored in this paper or in this study. This is called the ACC based approach, and this approach avoids direct power control. Instead, the controller emulates button presses to adjust the set speed and the time headway of the ACC. So, quickly, let's recall what ACC is. I'm sure a lot of you already know what ACC or adaptive cruise control is. So, fundamentally, ACC has two key components: the set speed adjustment button and the gap or time headway adjustment buttons. Whenever we press these buttons on our car, an electric signal is sent to the ECU of the car where a corresponding voltage describes which specific button is actually being pressed by the driver. Now, the goal here for this specific method is to mimic those button presses without actually pressing the ACC button, so that we can automate speed adjustment and gap setting adjustment without actually pressing the ACC buttons. The main design of this method is the use of a digital potentiometer. So the idea is that we wanted to put this digital potentiometer in parallel with the actual terminals of the ACC buttons. So whenever we press a button on the ACC,
Excuse
it
me, Joy.
yep.
Sorry to interrupt you. This is just a gentle reminder that 2 minutes are left for your presentation.
Okay, I think yeah, I'll try to to speed up. So again, when we try to press the buttons on the ACC in our car, it sends signals to the ECU corresponding to some value of resistance. So this is what we're trying to do by adding a digital potentiometer. We want the digital potentiometer to to output some value of resistance so that we can emulate the driver input, like as if it's pressing the set speed or the gap setting button. This leverages the OEM's built-in control logic while still allowing algorithmic decision making. And take note that we tested this external circuitry that we added to mimic the ACC button presses and confirm that they are working as designed. Now, quickly, we created a test. So we collected about 80 kilometers of leader-follower driving data. We allowed the controlled car to follow a leading vehicle that is manually driven, which is asked to drive in random pattern on purpose. So metrics that we look into this experiment to compare performance for both approaches includes acceleration behavior, time headway, and the transient response. Now, for the result, the first thing I wanted to show here is that the speed-based approach is more reactive. As you can see on the acceleration distribution, the speed-based approach has a wider acceleration distribution. This implies that the ACC-based approach creates a smoother trajectory. We can also confirm that from this cumulative distribution of the acceleration. Clearly, speed-based accumulate greater acceleration sooner than the ACC-based approach. Then we also look into the deceleration distribution, and the main takeaway here that we can see is that more events of aggressive deceleration is logged for the speed base. And then we also look into that time headway. And what we wanted to highlight here is that for the ACC based approach, minimal events log where for the ACC based approach has a time headway of less than 2 seconds, which tells us that the ACC based approach is better in keeping a safety gap with the leading vehicle, which is as expected because it's using the default ACC of the car. Then finally, we look into the transient response and we see that though speed based approach is more reactive, its steady state error in tracking target speed is larger. Overall, I think what I wanted to say here is that the ACC-based approach produces smoother trajectories, fewer heartbreaking events, and more consistent time headway. In transient response, speed-based reacts faster while ACC achieves lower steady-state error. As a summary, the study shows that real-world vehicle control is feasible without privileged access. Direct actuation enables precision and flexibility, while ACC-based actuation
Excuse
enables
me, Joy.
scalable deployment. Just one more sentence. Understanding the trade-off is essential for bridging traffic control algorithm from simulation into real traffic. And that's the end of my presentation. Sorry for going over time. Let me know if you have any question. Hi, Malinka. I think you're speaking, but your mic is off.
Joy, I want to ask one question. How does PID tuning affect inter-vehicle distance stability under sudden braking?
I'm sorry.
Yes, I'm asking about how does PID tuning affect inter-vehicle distance stability under sudden braking? How it can be handle this?
The tuning. Um, so right now, we just simulated a leader vehicle and an vehicle following each other, and we tried to tune it using that data. And again, this is just from simulation before we deploy it on the actual the real world testing on the road. And we can actually improve the this uh, gains by using probably an actual real world data. I don't know if I
Okay.
answered your question. Yeah, but
Okay.
yeah.
Okay.
Professor Malinka, do you have any questions?
Okay, I am just wondering what is the future work?
So this work is actually allowing us to test more controllers on actual car on the road instead of just testing them on simulation. So now we gave a platform on how we can control cars, production grade cars, using these two different approach. One is more complicated, the other one is more deployable. It depends on what we wanted to achieve. So
Thank
yeah,
you.
I think the to answer quickly your question, the future work is to be able to deploy more controllers that we design not just on simulation but on actual real world deployment.
Okay, great work. Thank you.
Thank you.
Thank you, Ms. Joy, Professor Malinka, Dr. Vijeta. Next, we have Pavel Sirenko presenting Distributed System for Collecting Road Traffic Objects and their use in navigation.
Hi everyone, thank you very much for the introduction. Let me start screen sharing. Just a second, please. So yeah, hi everyone. Thank you for the introduction. My presentation describes a distributed system for collecting and using road traffic objects from dashcams. The main purpose of this project is related with new approaches in geo-crowdsourcing. The pipeline includes on-device detection, road segment matching, and quality control for use in map updates and related services. So currently, navigation depends on road attributes that change often, for example, speed limits, restrictions, warnings, and temporary changes. Traditional date methods are usually slower and may have uneven coverage across regions because in the majority of cases it's related with human in the loop membership. So, and dashcams provide a scalable source of observations from many vehicles. The main problem is not only detection but correct road assignment. A correctly detected sign can still produce an incorrect map update if it's linked to the wrong road segment. Of course, currently there are many exciting systems like that, and in the majority of cases, they use one-way data collection. Platforms like Mapillary provide geotagged images and extracted features for downstream mapping workflows. Tools like, for example, CartaView or OSM Tracker support field collection, often with manual or community editing. In this work, collection, validation, road matching, update delivery, and so they are handled as one pipeline to fill in the gaps in OSM maps and OSM sources. The work has four main contributions. First, it's end-to-end loop because we collect, validate, update, and use the data. Second, it's road level matching based on GPS, heating, deviation limits, and OSM geometry because we can collect probably the whole possible spectrum of telemetry from the target devices. The third is on-device ML for detection and classification. under mobile hardware limits. And the fourth, an operational pipeline with monitoring and stored evidences. The pipeline starts so from the dashcam, from the vehicle. The dashcam SDK we have developed produces object observations with time, GPS positions, heading, speed, confidence of the objects which were detected on the board. The system uses event level outputs instead of continuous video streaming. After upload, observations are validated and linked to OSM road segments. Two delivery passes are used near real time tool to update monitoring system and scheduled map releases, because so we cannot insert all our new observations in real time into the maps. So because it's a very difficult task. So on device ML platform, it's just ordinary object detections and type classification. On mobile hardware, detection is combined with the whole spectrum of telemetry. Taken across multiple frames is used to make the final location more stable. The system sends event level telemetry rather than continuous raw video. And privacy sensitive content is handled on the device. So here you can see just the metrics of the detectors and classifiers. So it's nothing unusual. And the more important slide. So according to the operational dashboards are used to track long-term behavior, we made an experiment over 18 months. The system collected about 30 million object observations. And the dashboards track ingestion volume, active devices, and confidence over time. They also show regional coverage, including the 30-day country breakdown. These support detection of confidence drops, coverage gaps, and ingestion failures. And all these data which we have collected allowed us start the map updates over OSM sources, because when we have so much data and we have all road structures and geometry from OSM with the ordinary algorithms to match the way with the cyan, so we can just engage probably the highest level, a bit higher level of data text for the road maps. So raw observations pass through several processing steps before becoming final map objects. First, the system applies confidence, geo, and hidden checks. Next, repeated detection are merged using spatial temporal clustering and consensus across frames and devices. Then the sign effect is linked to the correct OSM segment, and conflicts such as speed limits mismatch are flagged. Because we have different sets of tools just to monitor the maps, where we can find, for example, different max speed limits from OSM or from our system, and just monitor the whole spectrum of the signs. And of course, each final object keeps evidence and metadata for later review. And unfortunately, this approach has a lot of limits. The main limits come from sensor noise and road complexity. Because of the GPS and hidden noise can cause incorrect road matching, especially in dense urban areas, parallel roads, and multi-level interchanges. Rain, 9 conditions, blur, and occlusion reduce recognition quality. The whole so the quality of this approach is totally based on computer vision part. And of course, there are different kinds of errors. For example, missing or incorrect OSM data can also affect matching and conflict checks because sometimes OSM doesn't have ways from, I don't know, new built area or something like that. So the presented system combines on-device ML, road-aware matching, and operational monitoring for large-scale road traffic object collection and validating using dashcam. I would say that future work includes better robustness, more object types, safer automation for OSM-related updates. And the main aspect is publication of the whole set of our tools for the OSM community, just to scale our integration and our experiments for the whole world. So that's all. Thank you very much. Probably, do you have any questions?
I have one question. You mentioned
Yes.
about machine learning involvement in this approach. What kind of machine learning algorithms you use, and also do you have some comparison about the accuracy of these algorithms? And also, what is your opinion about artificial neural networks? Because you have different objects and you have to prepare different tasks considering machine learning.
So yeah, thank you for the question. First of all, the ML part, it's an dashcam part because we used computer vision to detect the objects. And of course, edge devices, mobile devices, they have sharp limits, pretty sharp limits, and that is why we had to use small models like exquisite nets, like SSD mobile nets, so something extremely simple, extremely optimized for GPU usage on OpenGL or OpenCL even, because not all edge devices have the best supports of different layers. So, and also we had some thoughts to use ML for roadways and science clustering and matching, so science with the ways. And of course, there was a problem because the system has been designed to be used in the open source society. So that is the main reason why we developed that. And such algorithms we tried to use were pretty complex. And so for example, to start the only one iteration with the clustering of all these signs, so it's around 30 millions for the whole OSM worlds. There was pretty difficult operation with high demands for the cloud resources. And of course, we had to reduce some our expectations from the infrastructure, which will be used for the deployment of such things. And that is why we decided to leave our matching on standard mathematic methods like triangulations for broad traffic science, and we made the matching totally on just limits, so deviation limits, and the degrees differences between the limits, and so between the sign direction and the heading of the car.
Thank you so much for your answer.
Dr. Rosita, do you have any questions? Okay. Thank you, Mr. Pavel and Professor,
Thank you.
for the questions and the presentation. Next, we have Vasilina Vikova presenting natural language processing techniques in digital forensics, analysis and application.
Good morning. I will share my presentation. Good morning, dear chairman and colleagues. My name is Vasilina Vukova, and today I will present our paper titled Natural Language Processing Techniques in Digital Forensics, Analysis and Applications. This work was developed in cooperation with my co-author, Professor Malinka Ivanova. Thank you. I will start with the rapid expansion of digital data and cyber threats. Automated language technologies are becoming essential tools for investigators. This paper examines the growing role of natural language processing in digital forensics and digital forensic investigation. The study provides a bibliometric overview of current research trends and applications in this evolving field. As cybercrime continues to grow and become more complex, investigators rely more and more on AI-based tools to analyze large amounts of textual data. This study explores how natural language processing is used to support digital forensic investigations and highlights key trends and applications based on review of recent research. NLP makes it possible to efficiently extract useful knowledge from emails, documents, and social media content. Techniques such as name entity recognition, relation extraction, document classification, and semantic search help investigators quickly find relevant evidence. For this reason, the study focuses on how NLP is applied in digital forensics and summarizes current research in a conceptual model. The main objective of our study is to examine how natural language processing techniques are applied in digital forensics and digital forensic investigation. To achieve this, we conducted a semantic bibliometric analysis using the Scopus database and followed the PRISM framework to ensure a transparent study selection process. We used two keyword queries, natural language processing and digital forensics, and natural language processing and digital forensic investigation to retrieve relevant publications. The search was conducted on August 9, 2025, using the Scopus database. As I said before, we applied two main keyword queries. The initial search returned 114 documents for the first query and 16 for the second query, giving a total of 130 publications. Next, we applied filters for the period 2021-2024 and limited the results to English language open access publications. After applying the time filter, the results were reduced to 58 and 11 documents respectively. We also removed duplicate records and screened for relevance to improve the quality of the dataset. The Prisma methodology was used to systematically manage and visualize the selection process. Following the full filtering procedure, 20 studies were selected as the final dataset for the bibliometric analysis. From the overall bibliometric overview, the results show a clear upward trend in the number of publications, indicating growing scientific interest in the application of NLP in digital forensics. In the first query related to digital forensics, 58 relevant documents were identified, produced by 173 authors and published in 26 different sources. The second query on digital forensic investigation returned 11 documents from 44 authors across 8 sources. The growth rates of approximately 27.72% for digital forensic and 58.74% for digital forensic investigation further confirm the rapid expansion of research activity. High citation counts demonstrate the relevance and impact of the topic within the scientific community. Additionally, mass publications involve multiple authors, typically including 3 to 4 international collaborators, which highlights the strong global and collaborative nature of research in NLP-supported digital forensics. This section presents the geographic distribution of scientific production in NLP applications for digital forensics. For the first query on digital forensics, the dataset includes 58 documents produced by 173 authors, with the USA, India emerging as the leading contributors. They are followed by China, the United Kingdom, Sri Lanka, Germany, Spain, Turkey, and Indonesia, demonstrating broad international participation. For the second query on digital forensic investigation, the analysis.
Excuse me, ma'am, you're not audible.
I think some technical problem maybe.
Miss Lena, do you need any assistance?
Because I've got author.
Yes, ma'am. Sorry, I can't hear you. Your voice is echoing. Would you please repeat?
Yes, Veslina is present or not? I want to ask one question.
She was present, but I think there is some technical glitch due to which she cannot present right now.
Okay.
Yeah, actually, there is a technical problem with internet connection, but I'm co-author, so I can just summarize what is the work about. The main idea is to see how natural language processing techniques could support digital investigation, because this presenter, Evelina, not Evelina, Veselina, actually is my PhD student, but also she is a great investigator. Actually, he works on real cases in the practice. So actually, we wish to connect real practice with theory and technologies in the area of natural language processing. So the main idea is to explore actually what are the main techniques that we can use to support real problems in digital forensics. Also, we have several ideas for future work, how to implement our solution in real cases.
Sorry, my internet is crash. May I share again my presentation?
I'm sorry, miss. Your time for the allotted time is up, but Professor Malinka has summarized your presentation on your behalf. So we will be moving forward to with the questions.
I'm sorry. Thank you.
Dr. Vijayapur, do you have any questions?
To share again?
No, no, I'm asking the session chair if they have any questions. Okay, I believe there are no questions, so we will be moving forward with our next presentation. Right. We have Martin Michalovic presenting recognition of 3D identifiers in mixed reality systems for industrial applications.
Yes, good morning. Can you hear me?
Yes, you're audible.
Perfect. Okay, and can you also see my presentation?
Yes,
Okay, perfect. Perfect. Good morning. Once again, my name is Martin Michalovic, and I'm from the Faculty of Electrical Engineering and Information Technology in Bratislava, Slovakia. Today, I will present our paper titled Recognition of 3D Identifiers in Mixed Reality Systems for Industrial Application. I split the presentation into 4 parts, starting with motivation, then design of the identifier, recognition application, and finally I will summarize experimental evaluation. Augmented reality and mixed reality are closely connected with the concept of Industry 4.0, where the main goal are to optimize production processes and better respond to market changes. The use of AR helps employees improve their productivity, efficiency, and safety at work. A typical example can be use of AR glasses where the employees can see a real-time information in their field of view, such as work instructions, repair manuals, current state of devices, or can be used for interactive training. To display such virtual elements in real time, AR applications use different tracking and recognition approaches. One of the most common is marker-based AR. System use unique high contrast geometric patterns as reference points for the camera. Typical examples are graphic markers, QR codes, or barcodes. However, there is several limitations, especially in industrial environments. Recognition can be negatively affected by motion blur, poor lighting, or strong reflections. Also, in dusty environments, markers can become dirty or physically damaged. Disadvantage can also be their planar localization and tracking, or the ease of decrypting or copying them. To address these limitations, we propose the use of 3D identifiers as an innovative solution for object identification and localization in mixed reality environments. The goal was to design an object identifier which is not only recognizable by AR systems but also suitable for 3D printing. The advantage can be the possibility of scanning from any angle and different distances. They can also be useful for identical entities if they have a similar or the same physical shape or are dynamic. And with practical example of their application in logistics and warehouses where QR codes are commonly used. About the identifier design, at the beginning it was necessary to define what properties the identifier should meet. We decided it should be able to carry information. The question was how to make the design so that it can include ID or key information in it. Then we defined that the generated design should be or should reflect such coded information. It should also be suitable for 3D printing, and last but not least, it should be recognizable. We designed the appearance of identifier in the shape of cube. ID is entered by user as a numbered string of at least 7 digits that is converted into format that can be interpreted as a 3D shape. In our case, the number string is converted into square system where each bit is from the range 0 to 3, and each number from this range is represented by one basic element you can see here. Our program that is coded in a Python script in Blender environment then places together these basic elements to the scene, creating a cube identifier as is in the picture. Later, it is exported as a STL file from Blender, which is a standard format suitable for 3D printing. In our laboratory, we use these 3D printers Prusa for additive manufacturing. And as you can see in the picture, we were able to print several identifiers which were later used for the recognition. About the recognition application, the recognition application itself was built by using Unity together with the Vuforia engine for object recognition. The main idea behind the application is very simple and practical. After launching the application, the user loads a database containing all expected 3D identifiers. And when a physical identifier is placed in front of the camera, the system recognizes the object in real time and matches it with the corresponding model from the database. The application also displays the recognition time, which is shown in upper right corner of the screen. And the training itself takes place in the model target generator provided by Vuforia. In this step, the previously generated identifiers are uploaded to the system. For each identifier, we define basic rules and parameters that guide the creation of the database. Essentially, we upload STL files of the objects and software processes them so they can be recognized in real time. On the slide, you can see examples of STL objects that were loaded into the model target application. To validate our approach, we subjected the 3D printed identifiers to recognition tests. Each identifier was assigned with a unique name, which is displayed in the upper left corner of the screen when the system successfully recognizes it. A picture on the slide shows a preview of the setup in our laboratory, where we hold the device running the recognition application in our hand. And you can also see the 3D identifier in front of the camera that was successfully recognized. In addition to laboratory tests, we also conducted recognition tests in external warehouse as well. The goal of this test was to evaluate how well the system performs under real-world conditions, including different lighting, distances, and the background. So as you can see in the picture as well. What leads us to the evaluation? Our results show that the identifiers were successfully recognized in real time as well, confirming that the system is robust and practical beyond laboratory conditions. When testing in external environment, we observed an increase in recognition time ranging from 17 to 22% compared to laboratory conditions. But this increase is due to lighting, reflections, and background interference, which are common challenges in the real world environments. Nevertheless, the system demonstrated stable behavior with standard deviation values remaining below 0.15 per seconds per tested objects. And about the printing costs, it took around 1 day and 17 hours using 195 grams of filament to print one object or one 3D identifier that we used for the recognition. Thank you very much for your attention.
Thank you, Martin, for the presentation. Professor Malinka, Dr. Vijeta, do you guys have any questions?
Okay, please share your experience about some challenging issues.
Yeah, one of the most challenging issues was to define right shape and also the right balance between printing cost in terms of time and filament and the final object. Also the recognition in real time was a bit challenge due to fact that the environment in warehouses can be different, especially in terms of lighting.
Okay, and do you have any suggestions for good solutions of these challenges?
Yeah, we currently are working on small redesign of 3D identifiers to be more robust or more in terms of the pattern on their faces to be more robust. This should solve the problem with lighting conditions and to be recognition faster than it is now.
Thank you.
Thank you as well.
Dr. Vishwata, do you have any questions?
Can I have a question?
Yeah, sure.
I'm actually curious about how is the computation time or the processing time significant? Like how long does it take?
In terms of recognition or to create or print this object?
In terms of the recognition.
Yeah, from our experience, it took just a few seconds to recognize a specific identifier.
I see. Thank you.
Thank you as well.
Thank you for the questions, everyone. Now we have Alexander Gladly presenting the use of IoT devices and digital technologies of physical rehabilitation for the needs of elderly people in healthcare, services, and inclusive tourism. Next, we have Joy Carrillo presenting validation and calibration of energy models with real vehicle data from chassis dynamometer experiments.
Can you now see my screen? And can you hear me also?
Yes, your screen is visible and your voice is audible.
All right. It's me again. I'm gonna present the other paper that I submitted for this conference. And again, good morning. So I'll be presenting this time the result of my PhD research in collaboration with Temple University and Toyota North America. So this work is conducted in 2022. Um, I think I made this slide a little bit long, so I'll try to do it really fast. So the motivation of this work is the Circles project, which is the 100 controlled cars deployment on the actual road in Nashville, Tennessee in 2022, and um, this uh, this project tested a bunch of controllers in simulation, and they tried to evaluate it in a small scale experiment before they deploy it using a full deployment using 100 controlled cars. And the basic idea of this experiment is to capture the system level effect of a network of controlled cars deployed evenly spaced along a corridor. So one of the things that helps this project is the deployment of smart camera infrastructure that is capable of capturing high resolution video recording of vehicles on the road. So along a about 4 mile stretch of the I-24 interstate freeway on Nashville, Tennessee, they deployed this smart camera infrastructure in one of the important contribution of this sensing infrastructure is that it is capable of categorizing vehicle that it can see on the road based on type, as you can see on this slide. And the reason why this project tries to categorize the vehicles based on type is because of the idea that each vehicle type consumes energy in different ways. For example, truck surely consumes fuel in more significant, a larger consumption behavior than a sedan, for example. And so one of the thing that we bridges in this project is that we have to utilize that this output of the project wherein they can categorize vehicle by types by just looking on the camera system. Take note that the challenge in evaluating controller impact on energy efficiency is that there is not really an accurate or realistic energy models that is used to quantify the fuel consumption of vehicle by types. So most of the papers that evaluate energy impacts of controllers use kinematic proxies, for example, L2 of acceleration, or by just using simple power model that depends on just acceleration or speed. And so what we're trying to do here is that we wanted um, the evaluation to be more realistic and more accurate by understanding that different types of vehicle consumes different way, or different types of vehicles consume energy in a different way. As you can see in one of this plot that I put here, when we try to assess the energy saving tendency of different types of vehicles, we see a clear clusters, and from each of this cluster we try to get the centroids, and we were able to see some representative. And so another important contribution of this project, the Circles project, is the creation of these energy models, wherein from the representative vehicles we try to model the energy consuming behaviors of each of those vehicle class. And take note that the list of vehicles that we choose from is coming from the library, from this simulation tool called Autonomy, which is a highly principled simulation tool developed by Argonne National Library. And and again, we were able to derive six representative energy models from those.
Joy, I want to ask one question.
Yep.
What are the key parameters that requires calibration to reduce prediction error in energy models?
So I was going to discuss quickly the modeling pipeline. So in the previous slide, I was talking about the autonomy. This is already an established simulation tool, but the problem with this tool is that you can only input like a driving pattern, and it will output the fuel consumption one at a time. So one driving pattern, you will get an output after, and it takes so much time for us to be able to get a result. And if we wanted to analyze the energy impact on an entire traffic fleet that has thousands of vehicles, we want to have an energy model that is fast computing. And so from this autonomy, we try to model a simplified model that is that can calculate the energy consumption of hundreds or thousands of vehicle in a simulation or an actual vehicle data, which the smart camera system can capture in a span of few seconds. So this pipeline uses the autonomy, and from this highly principled model, we were able to develop a simplified model. There is a specific paper that talks about this energy modeling pipeline, but I just wanted to emphasize here that we utilize this pipeline to do the validation. That is the main topic of this paper. So from autonomy, we generate that. Sorry. And sorry. Sorry, my dogs are they woke up. So from autonomy tool, we generate data from that, and we use those data to create a polynomial pitted function that estimate the energy consuming behavior of different types of vehicles. And I wanted to do it really fast because I think I made the slide so long. So from autonomy, we extract maps from that tool, which allows us to create this semi-principled model. So we call it semi-principled because it designed a model that is still using physics reasoning, but using fitted maps so that the computing can be faster. But when you're using multiple pitted maps in a model, there could be an obvious discontinuity. And so we try to improve that a little bit more by fitting the output of the semi-principled model into a piecewise polynomial functions, and leads us to the development of these simplified models. Now, at the end, we try to compare the output of the simplified models to the output of the autonomy tool, and we see that there is a good agreement, but take note, the result of the simplified model is only validated on a simulation tool. We want to validate it into with an actual vehicle data. And so to be able to do that, we executed this chassis dynamometer experiment wherein we put a car on a chassis dynamometer. We drive it in different driving patterns, and but the question maybe is, how do we compare the data from this actual car to your model? And to be able to do that, we need to have an autonomy model version of that specific car that we are testing. So we created a dedicated autonomy model for the Toyota RAV4 that we tested on a chassis dynamometer. And from that autonomy model, we replicate the same energy modeling pipeline to generate a semi-principled model and a simplified model, from which we can now compare with an actual dynamometer data, or the data that we generated from the dyno experiment. Now, for the validation, so just a quick recap. So we created a dedicated autonomy model on that tool that is specific for Toyota RAV4. And since in the energy modeling pipeline, we said if you have autonomy model, you can generate a semi-principled model, which leads to a simplified model. So now that we have an autonomy model, we are now able to generate or to obtain those reduced models, energy models. Um, to validate the energy models that we created with an actual vehicle data, we use this validation metrics. So we compared the fuel rate consumed by the Toyota RAV4 recorded on that dyno experiment. We also was able to record internal dynamics like the engine speed, the torque, the pedal angle, the gear scheduling, and things like that. And here I just wanted to show you the comparison of the autonomy model that we created specific for the Toyota RAV4 versus the data that we extract from the dyno experiment. So the dyno experiment is the actual vehicle data. And as you can see here, there are some discrepancy here. The gear selection has some discrepancy, and so we try to improve it a little bit more. If there is a discrepancy in gear selection, it will affect also the estimation of the engine speed. That's why you see some discrepancy here. So we try to improve it a little bit more, and now the improved autonomy here, you can see that the gear scheduling has more agreement now, which improves also the fuel rate estimation.
Excuse me, Joe.
Yep,
Um,
2 minutes.
just a reminder, 2 minutes are left.
Yeah, okay. Now, so after we improved the autonomy model that we did specifically for a Toyota RAV4, we obtained the semi-principled model from that and compare that to the dyno data. So here is just a comparison of what the fuel rate estimated by the model, the semi-principled model, and what is actually consumed by the car. And so this is for a steady driving pattern, the highway HW FET, and this is for a more aggressive driving pattern. I think the main takeaway here is that um, we are struggling to model uh, a more aggressive driving pattern, but for steady driving pattern, we are doing really good. And finally, for the simplified, which is the final output of this modeling pipeline, what we wanted to show here is that you see here, the yellow one is the simplified model. It has more or better agreement with the actual dynamometer data. In the end, what we wanted to say here is that if we have a good calibration, or if we have developed a good autonomy model of a specific vehicle, we are confident that the resulting simplified model from that one, which is a fast computing, easy to optimize structured model, is will result to an acceptable or a reasonable, realistic estimate of fuel consumption for that specific vehicle class. Um, Yep. I think that's the end of the presentation. I'm sorry I did not time this presentation well, but I hope you were able to get the meat of the presentation. And thank you for listening. Let me know if you have any question.
Thank you, Ms. Joy, for
I have one
your
question
presentation.
about the calibration process.
Yep.
Do you have several solutions, approaches for calibration?
So the only calibration that we did here is that so the autonomy is a tool, so we just feed it with the drive cycle, and we see the output internal dynamics, the output fuel estimate, and we compare it to the actual data from the car, and we just do the tweaks from there. For example, we see that the gear scheduling are not matching, so we try to adjust how we decide the gear scheduling on the car on the autonomy side. By the way, maybe this is confusing. Autonomy is a tool that is Simulink based, so you can change and tweak things inside of it. That's so. For example, I can change the tire radius because Toyota RAV4 radius is this much, so I can change those parameters in that tool, so that we can make it very specific and matching the property of a Toyota RAV4. Um, so yeah, we just use the actual vehicle data to tweak the autonomy model, because at the end, what we wanted to show is that if we have an accurate representation of this car in autonomy, then I can derive a simplified model that is accurately um, estimating the fuel consumption of that vehicle. I think that's the bottom line of this validation test.
Okay, thank you, thank you.
Mm-hmm. Okay, thank you so much for listening. If you have any more questions, feel free to email me, or if not, then I'll pass it on to the moderator.
Joy, I want to ask one question. What are the future research direction to you for say energy model validations?
What are the future research?
Yes.
So I guess we wanted to improve how controllers are being tested or evaluated in the past, before they just see the trends of acceleration and say, oh, we were able to improve the energy efficiency. But in reality, that doesn't necessarily say something. So here we wanted people to actually look into the actual trajectory of the car, and using these energy models we can tell whether the energy efficiency actually improves or not, and not just relying on some generic proxies. And take note, different cars behave differently. In one of the plots that I showed on my presentation, some cars behaves better in city driving, for example, but do worse on a highway driving, which is, if we will just rely on acceleration proxies, we always say that cars behaves on highway driving than city driving. So those are one of the findings that we see, that why we think there is a need to actually know to represent energy consuming behavior of vehicle classes by type.
Okay, Joy, now very nice presentation.
Thank you.
Thank you, Ms. Joy, for the presentation, and Professor Melinda and Dr. Vijayata for the questions. We're done with all the presentations for today. I sincerely thank all the authors for the excellent presentations and valuable contributions to this session. I also extend my gratitude to all participants for being a part of this international conference. I hope this session was informative as well as insightful. On behalf of the ICICT team, thank you for your continued support during the 11th edition of ICICT, as well as all the previous editions. We look forward to welcoming you again for the 12th edition in 2027. All presenters will receive their digital certificates via email within 2 working days. The publication is expected to be available within 7 to 8 months. We kindly request your cooperation with the ICICT 2026 team during this process. I'd also like to thank our session chairs for effectively sharing this session. And as a token of our appreciation, we'd like to present this on behalf of the ICICT team and GR Scholastic and Foundation. Professor Malanka and Dr. Vijayka, would you like to share a few words or closing remarks?
Okay, dear colleagues, dear presenters, we saw wonderful ideas, models, experiments, maybe future improvements and innovations in different areas. So I would congratulate you and also to wish best achievements in the future that maybe you will share with us in this or other conferences. Thank you again. You were wonderful. Thank you.
I would also like to thank all the audience for active participations and thoughtful questions which made the session highly engaging and productive. Thank you once again to everyone for making this session a great success. Thank you all the organizing committee members.
Thank you for your kind words, ma'am. May I please request everyone to turn on your cameras so that we can have a quick snapshot of the session? Thank you everyone for joining us today. Have a great day.
Have a great day.
Thank you.